By late March 1941, the impact of Beatrice Shilling's restrictor was becoming apparent. The first Hurricanes equipped with her brass washers had flown multiple combat patrols without a single engine failure. Squadron leader Davies's section had successfully completed 12 dives on Messerschmitts, each time pushing their Hurricanes to full throttle and steep negative G maneuvers. The Merlin engines performed flawlessly. Pilots reported that the engine seemed almost more powerful at altitude, though in truth, the fuel flow had merely been stabilized. Word spread quickly from squadron to squadron. Pilots who had been hesitant to press diving attacks began requesting aircraft with the restrictor installed. Others refused to fly missions until the modification was fitted. Shilling received phone calls day and night from commanding officers and ground crew sergeants at stations across southern England. Each request emphasized urgency. How soon could she visit? How many restrictors could she bring? Could her small team oversee installation at remote airfields? The answer was clear. Mass production was required immediately. Shilling had machined 6 restrictors herself, enough for testing and initial deployment, but not nearly enough for all operational aircraft. She drafted a proposal for the Air Ministry, detailing the modification, its design, simplicity, and the measurable results. She emphasized the immediate life-saving potential and the rapid installation time, less than 15 minutes per aircraft without removing it from service. 4 days later, the Air Ministry approved her plan and fast-tracked production. Rolls-Royce received the contract and could manufacture 500 restrictors per week. Shilling assembled a small team of engineers and mechanics, ready to oversee installation at RAF fighter stations. The rollout began at Biggin Hill, the busiest fighter station in 11 Group. 32 Spitfires, 21 Hurricanes, and 4 rotating squadrons depended on continuous operations. Station Commander Group Captain Grace, who had lost 7 pilots to engine failures in just 2 months, greeted Shilling personally. He watched as ground crews worked in shifts, installing restrictors in groups of 4 aircraft. Each installation required precision, disconnecting the fuel line, sliding in the brass washer, welding it in place, reconnecting, and testing for leaks. Any faulty weld could starve the engine completely at altitude. Shilling supervised every stage, checking each weld herself. She rejected 3 restrictors that failed to meet specifications. Pilots observed with intense interest. Flight Lieutenant James Lacey, 41 combat missions, had experienced engine failure twice during dogfights. He asked Shilling how a simple brass washer could solve such a complex problem. She patiently explained fuel flow physics, float chamber dynamics, and the effects of negative G. Lacey, an engineering graduate from Cambridge, immediately recognized the brilliance. He called it elegant simplicity, an apt description for a wartime innovation that combined precision engineering with practical problem solving. By March 28th, all 53 Merlin engines at Biggin Hill had been modified. Shilling moved on to Hornchurch, North Weald, and Tangmere, repeating the process. Ground crews worked 12-hour shifts, installing 4 aircraft at a time. Combat patrols continued uninterrupted, and the results were immediate. Pilots flew diving attacks, climbed aggressively, and tested their engines to the limit. No failures occurred. Word of the restrictor's success traveled faster than the component itself. Pilots began referring to it affectionately as Miss Shilling's Orifice, a nickname coined by Sir Stanley Hooker, chief engineer at Rolls-Royce Supercharger Division. Shilling, familiar with military humor, accepted it with good grace. The nickname helped pilots remember the modification, and that was all that mattered. By early April, the restrictor had been installed in every operational Hurricane and Spitfire in 11 Group. 2,100 Merlin engines across multiple airfields had been modified. Fighter Command observed a dramatic improvement in combat statistics. Before the restrictor, engine failures occurred in 38% of diving attacks against German aircraft. After installation, the failure rate dropped to 0.4%, almost entirely eliminating the previous vulnerability. The kill-to-loss ratio improved drastically. In March 1941, RAF Fighter Command had lost 47 aircraft in combat while destroying 61 enemy planes, a ratio of 1.3 to 1, barely breaking even. In April, after the restrictor rollout, British losses dropped to 29, while German aircraft destroyed increased to 94, a ratio of 3.2 to 1. The restrictor was not the only factor, but squadron commanders credited it as a major contributor. Confidence soared among pilots. They pressed diving attacks without hesitation, knowing the Merlin engines would not fail at the most critical moment. Flight. Lieutenant Robert Stanford Tuck, based at Duxford, had experienced engine failures 4 times prior to the restrictor. After installation, he aggressively engaged the enemy, shooting down 3 Messerschmitts in May and 2 more in June. He attributed his ability to press attacks to the stability provided by Miss Shilling's orifice. The modification spread beyond fighter command. Coastal Command requested restrictors for their bow fighters. Bomber Command wanted them for training. Aircraft, and even the Fleet Air Arm, inquired about installation on carrier-based fighters. Shilling coordinated production with Rolls-Royce to meet growing demand. By June 1941, manufacturing output had increased to 1,000 restrictors per week. Installation could be carried out without removing aircraft from service, ensuring continuous operational readiness. Pilots and ground crews trusted the modification. If it worked, there was no need for further changes. During the summer and fall of 1941, Shilling's team continued to monitor the restrictor's performance. Reports came in from every fighter station in southern England. 0 engine failures during negative G maneuvers, improved dive attacks, and higher pilot morale. Pilots who had been hesitant or nervous about aggressive tactics now pressed attacks with confidence. German intelligence began to notice the shift in RAF performance. Luftwaffe after action. Reports noted that British fighters no longer broke off pursuit during dives. Messerschmitt pilots could no longer exploit the carburetor weakness. Tactical advantages shifted in favor of the RAF. Meanwhile, Shilling did not limit her work to the restrictor. She tackled multiple critical engineering challenges during the war. Cold weather operations were a constant concern. RAF Spitfires deployed to Iceland and Russia faced extreme winter temperatures. Engine oil thickened. Fuel lines froze, and batteries died. Ground crews unfamiliar with Merlin engines struggled to start aircraft. Shilling developed cold start procedures using preheated oil and modified fuel mixtures. Her solutions enabled Spitfires to fly combat missions reliably in sub-zero conditions, a vital contribution to the Arctic campaign. She also addressed high-altitude performance problems. Late-war Spitfires operated above 30,000 feet, where thin air reduced oxygen levels, and required precise fuel mixture adjustments. Engines either flooded if too rich or overheated if too lean. Shilling designed carburetor modifications that improved power output by 8% above 30,000 feet, giving pilots critical performance advantages at extreme altitudes. Despite her intense professional life, Shilling maintained a separate personal life. She had married George Naylor in September 1938. Naylor, an aerodynamicist at the Royal Aircraft Establishment, volunteered for RAF Bomber Command when war broke out. He flew Avro Lancasters with 625 Squadron, completing 31 combat missions over Germany. He earned the Distinguished Flying Cross for completing an extra tour beyond his required missions. Shilling worried constantly for his safety, understanding the high casualty rates among bomber crews. 1 in 2 did not survive the war. Naylor beat those odds, returning safely in 1944. The couple never discussed wartime operations. Professional and personal lives remained compartmentalized, allowing each to focus on their responsibilities without distraction. Shilling continued to ride her Norton motorcycle whenever possible, a habit from her youth and racing days. She often solved engineering challenges during long rides, thinking through complex problems while traveling at high speeds. Some of her most innovative ideas originated while navigating country roads at 90 miles per hour, using intuition honed from decades of engine experience. By 1945, she had contributed to 17 major projects, including cold weather systems, high-altitude carburetor improvements, fuel mixture optimization, and supercharger efficiency upgrades. Each project saved lives, ensured aircraft remained operational under extreme conditions, and maintained RAF combat readiness. The war ended in May 1945 with Germany's surrender, followed by Japan in August. The Royal Aircraft Establishment transitioned from emergency wartime projects to peacetime research. Shilling remained at Farnborough, fully committed to engineering. In 1948, she received official recognition for her wartime contributions. King George VI appointed her an Officer of the Order of the British Empire. She attended the ceremony at Buckingham Palace, wearing formal dress, accepted the medal, posed for photographs, and returned to work the next morning. Recognition did not alter her dedication to solving technical challenges. She continued hands-on engineering projects, preferring direct engagement over administrative roles. Shilling's career continued for another 21 years at the Royal Aircraft Establishment. She worked on the Blue Streak missile program, focusing on fuel delivery systems and high-altitude performance. She researched wet runway, braking effects, crucial for reducing landing accidents that killed more pilots than engine failures by the 1950s. She published technical papers, contributed to bobsled design for RAF Olympic teams, and mentored younger engineers. Yet, her most famous contribution remained the brass restrictor, affectionately called Miss Shilling's orifice. It was a small, elegant solution to a complex problem, implemented under wartime pressure with measurable results. Pilots remembered it, engineers studied it, and schools taught it as a model of practical, life-saving engineering. By the end of the war, Shilling had firmly established herself as a pioneering engineer. Her restrictor had transformed RAF fighter performance, saved countless lives, and demonstrated the power of innovative problem-solving under pressure. The modification's impact was quantifiable. Fighter command statistics showed drastic reductions in engine failures, improved pilot confidence, and superior combat performance. Miss Shilling's orifice became an iconic example of simple, effective engineering in the face of urgent wartime challenges. She had proven that practical innovation, combined with technical expertise and courage, could decisively influence the outcome of conflict. Her legacy extended beyond the war. Museums displayed original restrictors, universities studied them, and pilots recounted their life-saving effects. Shilling had shown that one engineer, working with focus, skill, and determination, could make a tangible difference on the battlefield. The restrictor became a teaching example worldwide, embodying principles of elegant engineering, rapid implementation, and measurable success. It was a reminder that sometimes the simplest solutions can have the most profound impact.